recording is on, you can start.
Yeah. So in this presentation, I'll be covering a paper called Harmonic Neural Networks, Deep Translation and Rotation Equivariance. This is a paper presentation. So it's more similar in genre to neural tangent kernels, neural tangent kernel session than to the topology and rep theory sessions. I will be drawing on some of the material from the presentation theory session, so stuff like irreducible representations, group Fourier transforms, basic stuff like that. It's not essential, but it's mentioned a few times. But you can go through it without knowing graph theory. Okay, then I'll start. Suppose we're training some neural network. We are trying to approximate a function using some other function. And we do this by looking at some limited sample on distribution. We can't sample every point, we are limited in data, and this results in an imperfect approximation. And we want to improve it, so we can, for example, take advantage of some symmetry. Um, a symmetry like translation. If you take this image of a zebra and you translate the zebra a little, then it's still an image of a zebra in the savannah. Um, and this is something called an invariance. Our function, which classifies an image, its output doesn't change if you apply some action to the input data. Um, and when talking about invariances, we use the language of group theory. We say that something is invariant with respect to a group. So for any action in that group, our function will have the same result. Um, yeah. Um, so suppose we have those images of zebras translated a little, um, and we want to train a network that can take advantage of the symmetry to overcome our limited data problem. We can take some, I don't know, MLP, and we want to make use of our knowledge that there is a symmetry in the data. We can try to augment data. So take a single sample and generate many copies of it and train with that. And of course, people do that. This works, but there are two problems which motivate equivariant neural networks. So first of all, when you just augment data and let the network figure out how to learn to be invariant, you'll get duplicate filters. So for example, if your neural network is trying to detect a curve in an image, it will try, naturally learn filters that represent this curve at every possible rotation. You get duplicate filters for the curve. This is an actual phenomenon that has been studied for Inception V1, and it just learned that on its own with ImageNet, which is not even augmented. Um, our network will learn curve detectors in the third layer, and there's a lot of redundancy. Uh, and there's a whole paper about this, which would not have been necessary if you had some way to make the network respond to all images that are rotated copies of each other equally, without it learning to do it on its own. So with equivariance, it's easier to do interpretability. You get less filters. Another issue we have with this kind of invariance achieved by training on augmented data is that your learned features won't stack with other things. So for example, you've learned your zero detector. The final layer, you have a feature map where for each pixel you have some feature, a small vector. And suppose you want to put a segmentation head, like a linear layer that goes from every pixel to a probability that a zebra is in that pixel. And you do not have any guarantee that this penultimate layer will have uh, something that's equivariant. Uh, I haven't defined equivariance yet, but just as an intuition, when you shift your zebra a little, uh, your MLP with a segmentation head will not produce the a segmentation map that's shifted a little in general. Um, so what we can do instead is try to make the network equivariant. Equivariance is a property of a function which says that for any group elements, if you transform the input with that element um, and you map the translation through the function, you get some other image. Or if you take the original image and then get features and then translate them using the same action, you'll get the same thing. So basically, your transformations before and after the function, they commute. Um, Equivariances can help us solve this segmentation problem because you can, whenever you take two equivalent layers and you stack them together, you get another equivalent layer. So you can build up a network built of equivalent layers that is self-equivariant. You can stack something on top of that, and the segmentation will also be equivariant. And of course, with equivariance, you can get invariance without having to augment data. If you take some equivariant set of features and put them through an invariant final layer, for example, summation, like pulling NCNNs, you get an invariant function. So this is just the context and motivation for this. And one last thing about equivariance is that when you train neural network with it, you can get better results with less data in two ways. It's both true that the network has more knowledge at the start, and it also has higher scaling exponents. So it will get better and better with more data in a power law dependency compared to a regular non-covariant network. Uh, and It's been only recently proven when people started paying more attention to scaling laws. Um, but this should also be true for example, comparing covariant networks like convolutional networks to MLPs. So covariance has all these sorts of nice features. How can we get it? So suppose we have some linear feature extractor that works on MNIST digits. So um, it is a linear function that maps from pixel space to pixel space. Uh, and it's not covariant. And we want to make something equivariant using it. Um, there is a way to do this. We perform a lifting transformation. So instead of operating on images, we operate on all possible copies of an image transformed using all possible actions. So this is a representation of what it looks like for MNIST images and the translation group. And I should say that these next two slides, they are like an original explanation the way I first understood um, convolution as equivariance, and it is not very connected with the rest of what's going on. It's just to give better motivation for why convolution is equivariant. Okay, so we have those transferred copies, the Lifted space. And now instead of applying the linear transformation to just one image, we apply to all images. We map it to each. We apply to each image individually. Um, now, uh, uh, yeah, and actually, you can make this thing is equivariant because um, when you apply some group action to the original image, you just get some translated version of these duplicated copies. So in the end, you also get the same thing. And if you apply some the same linear transformation to those images, uh, you can turn this into convolution um, just by canceling some terms and multiplying them by values of filters in previous layers. But this is not very similar to what actually happens in convolution. You don't shift an image many times and then multiply it by some filter. Um, and here's why how we get from that to our original convolution. Um, at the end of our transformations, we get some set of group actions, and for each group action, we have images, and we want to get to pull all that. We want to go from that to a single number. And we could apply mean pooling, but then all images will map to the same thing because they're just translated versions of each other. Uh, so they will have the same mean. So we want some kind of dependence on the group action. We can just take the top left corner of each image. And if we do that, we get something like this. So for each group action, we have a single pixel. Uh, So at the end, all that really matters when we finally, at the final layer, pull those images together. All that matters is one layer of each pixel. And then we apply some pooling on the group elements themselves. And uh, for uh, um, for translation equivariance, this just works. We just reconstructed 2D convolutions by trying to make a linear layer equivariant. Um, but there's this does not extend to other transformations. If you look at something like 90-degree rotations, if you use this way of making a linear function equivariant, you will just apply the function separately on each rotated version of the image, and you will not have any lateral connections between different rotated copies. This is not very interesting, and it's not like real equivariance. You can pull them at the end, and you'll get something equivariant, but it's not um, true equivariance. It's not what we mean when we say that. So instead, imagine that we go back to our 2D translation case. Um, we can, instead of convolving little images, we can convolve group elements with nearby group elements. So the uh, definition of convolution now changes to what is commonly used. Um, and our feature maps now become not little sets of images, but mappings from group elements to complex numbers. And our filters are now also mappings from elements of groups to of a group to complex numbers. Yep. Um, that wasn't. Do you want to ask a question?
I think it was AI waifu joining in, but I think Hawk and might have a question.
Yeah.
just said I am confused in the meeting chat, but then uh, didn't elaborate.
Ah, yeah. I might
I
have
think maybe we
explained it
can
confusingly.
let him write his question, and then we can address.
Yeah, okay, I'll
You'll
wait.
submit it. Maybe just get back into the presentation.
Oh, wow, that's a lot of people.
Don't worry, it's perfectly normal.
Okay, lots of people are confused.
Yeah, so this is the math reading group, and Lev is presenting on uh, harmonic networks. So basically CNNs that handle rotation. Okay, so
Previous point about linear transformation.
about
Um,
the convolution
yeah,
or
really, if you did not find it useful, you can just ignore it. Um, Equivariance, uh, it's not um, variance under some group op. Uh, it's more that they apply to different kinds of functions. Um, well, equivariance is invariance is a stricter condition. Invariance means that when you apply some transformation, any transformation from a group to our inputs, you will get the same output out of function. And
yeah, maybe if you go back to the slides on equivariance, that might be
yeah,
clearer.
and covariance just means that for every input mapping, there is some output mapping such that you get the same result when you either apply the output mapping to the results of the function or the function to the results of the input mapping. So something like a 2D convolution is equivariant. Something like uh, taking the mean of all pixels is invariant.
Yeah, invariant would be the case where you want your representation to just not care at all about the translation. So it would be invariant would be the points just staying at the same place.
Yeah.
Maybe you can just like go back on your slides because I have also on the recording the chat, so it's like duplicated.
Ah, okay.
But yeah, go on.
Uh, yeah.
So yeah, hopefully I can you can hear me correctly now because Hawk mentioned I was barely hearable.
Mm.
But yeah, keep going.
Okay. So just to recap what happened, um, if you don't want equivariance, you can just have linear mappings from um, uh, the set of images to the set of images. But if you want equivariance, you need to do a group convolution. A group convolution is a generalization of 2D convolutions. It's a subset. Group convolutions are a subset of all possible linear transformations. Uh, Group convolution of for all group elements, um, it's it does a weighted sum. For all group elements, it weights the value of our function at that element um, by kernel weight um, at uh, um, the corresponding uh, filter location. So, for example, if our G is this pixel, um, then FKH is just one. Um, phi k is the value of the kernel at um, say this pixel, um, and h is this pixel. And we find this pixel by applying the um, inverse of our original group elements. So we first translate back here, and then we multiply this by our filter element to get this pixel, and we multiply by that. So if our kernel is this group of pixels, then this just produces the 2D convolution. And actually, it turns out that um, group convolutions are just literally all linear transformations that preserve group covariance. So even for say translation and 90-degree rotation, the group convolution for that group will be the only set of linear equivariant transformations. So if you want to make a convolutional network on this group, you'll have to use group equivariant convolutions. And this is the proof of this theorem from a paper. It basically just says that uh, um, given some elements of a group that you apply a function to, you can represent a linear mapping as some kernel that mixes in values from other group elements. It's not necessarily equivariant. Um, and on the left hand side, we have the image before the filter has been transformed. On the right hand side, we have what happened to the image after the filter. And we represent that by shifting the target and the source locations, respectively. Um, and we then uh, um, just find that the equivariance condition means that our kernel is also equivariant to actions. So we can take any action of two elements, and the kernel's value will stay the same. And then we rewrite the kernel in terms of uh, just taking a single element in. So in our 2D translation case, if before the transformation we had a kernel that could map from a source pixel to any possible target pixel, and the kernel could shift depending on what pixel you were convolving at. After the shift, we just depend on the value of the kernel at some location, um, which is this number of pixels in the illustration we had before. We just take the kernel between the identity and the composition of two actions, and we get the same thing. Um, and when we simplify, we get the same equation as before. With the function value and the filter value at g-1 g prime, and it's the same thing here, just with an integral instead of sum and different variable names. Okay, is this part clear about why group convolutions are um, the only possible linear mappings that are covariant?
clear enough, at least if you follow the representation theory stuff.
Well, we haven't gotten into representation theory yet.
Yeah, but at least if you like for people who had followed the
Yeah.
representation theory, they already know a bit about the group convolution.
Okay.
But yeah,
So then we had a 90-degree group. If we do a group convolution, we're only multiplying the amount of multiplications by 4. It's not expensive, but suppose we wanted something like equivariance to all, say 90 degrees of rotation or all possible rotations. Um, and in the first case, this will be very, very expensive. And in the second case, you just can't do that at all. Um, you can't just keep on discretizing if you want very high resolution. So instead of doing an naive group convolution, we can use representation. Um, so we will apply a Fourier transform instead of just doing naive convolution. Uh, but of course, you can't apply Fourier transforms to 2D rotated images. It's just not what Fourier transforms are suited to. Uh, no, it's not just a type error, sorry. And uh, instead, we'll use group Fourier transform. And uh, group Fourier transforms, they act on representations. And as a reminder, representations are homomorphisms from group elements to linear maps on some vector space. Or in other words, they're just a way to map group elements to matrices such that composition of group elements is a product of those matrices. Um, and an irreducible representation is one which is possible to map to another representation using an invertible matrix. Uh, so we have some representation of a group. If we have a circle, for example, um, or no, a closed interval of a real number line, our representation will just be the Fourier basis. Um, so when we have a representation, we can uh, define the Fourier transform of a group. Um, and a Fourier transform is taken of some function. So we have uh, yeah, if you have a function, you want to take a Fourier transform of it, um, you just multiply the value of the function by the group, the representation of a group element uh, for every action, and you sum them up, and you get some matrix. Um, and uh, sometimes you can map back, like for the Fourier transform, we can just use an inverse Fourier transform, which is also defined for groups. Um, and for groups, we have this old definition of convolution. It turns out that the element-wise products of two Fourier transforms of two functions is the same as the Fourier transform of the convolution of those two functions. So you can first take Fourier transforms, multiply them element-wise, which is less expensive than convolving, which is like um, n squared instead of n in the 1D case. Uh, and if we have all those things, we can compute group convolution more efficiently. And we can mix those together. So we can just, if we have both translation and rotation, covariance, we can slide through positions and then apply rotation covariance uh, convolutions using the Fourier transform. In the paper, we don't actually use the Fourier transform explicitly, but we use its properties. Okay, so let's go back from our example with both translations and uh, rotations, and go back to just rotations. Rotation symmetry means that you have some 1D function on a circle, and if you rotate it, it will be the same thing. So um, rotation uh, um, symmetry corresponds to the circle group, and for that we have um, a set of reducible representations, which is the Fourier basis. Um, the Fourier basis is just what you get when you try to find the reducible representations of the circle. Um, and you get a set of basis functions that go from points in a circle to some complex number. And for every integer m, both positive and negative, you will get a corresponding circular harmonic. And they're just the same thing as um, the Fourier basis. And they have all sorts of nice properties. Of course, they're periodic. Um, they are solutions to a lost equation, which is not relevant here. The product of two circular harmonics is also a circular harmonic. Um, I mean, the convolution. And we have the convolution theorem. So we can use them to calculate convolutions on the circle faster. And there are also a set of reducible representations. So all properties of the Fourier transform apply here because they're just the Fourier transform. And one interesting fact about circular harmonics, which is used in the paper, is that um, when you take one point in a translation and rotation group, and you take and you convolve it with the rest of the image um, using a circular harmonic. Um, the way they define convolution, they call it cross correlation, but it's really just convolution. They don't conjugate any arguments. Um, and uh, they look at just one possible radius for a 2D image. Um, and then if you have a circular harmonic that you're convolving a 2D image by, then rotating the original image around the point by some angle, and then cross-correlating it using the circular harmonic, you'll just get the same thing, but multiplied by e to the im theta. So rotating the original image around some point will also rotate the resulting complex number. I'm sorry, this was supposed to be some dramatic pause, but I'm too tired to do this properly. Um, yeah, and this is important because this is just covariance. Uh, you can use this property to achieve covariance. I will explain how in the next few slides. And here's a quick proof of this. Uh, write down the circular harmonic as a decomposition into some radius and circular harmonic itself. And then they pull out the factor corresponding to our rotation. Um, and yeah, it's pretty trivial. And another interesting property of circular harmonics um, that they use in the paper, well, it's just the same thing as with Fourier transforms. Uh, um, summing um, the circular harmonic representations of two functions will result in another circular harmonic representation of the same order. Um, and they represent orders using the letter M, which of course can be both positive, negative, and zero. Okay, so let's go back to harmonic networks. Harmonic networks uh, are they use group theory and circular harmonics to uh, create an equivalent feature mapping and then use it to make an invariant function. Uh, what harmonic networks do is use the lifted representation trick. So they compute features for all possible rotations. And of course, they don't store those features explicitly, but they use the value of the image at the top left pixel after rotating and translating it by all possible group elements. So our image is not really an image. It's a function on a circle uh, for each pixel. So it's really 3D, but they represent this third dimension in a clever way. Um, if you have this kind of representation, then you can just do convolution, group convolution in those 3D representations, um, and get equivariance. Um, so they, of course, don't represent this whole 3D thing. They represent the function as a set of circular harmonics. So for each pixel, you have coefficients of a few circular harmonics. They use the zeroth, first, second, and third um, in most cases. They have each pixel be a center of rotation. Um, what this means is that when you rotate the image around that pixel, um, and put that through the equivariant feature extractor, um, you'll get the same thing as if you didn't rotate it, but multiplied by e to the 2I pi m theta. So it's rotated by the order of the representation. So if you have a zero order representation, then it just doesn't change at all if you rotate it. So like in our original image, if you rotate it around some pixel and take the value of that pixel, it doesn't change because it's center of rotation. It doesn't change. But at the first order, for example, you'll get it rotated by e to the pi I. So all rotations of the input will be reflected um, in the phase of our um, circle harmonic coefficient. So we have this field of circular harmonics, and if we take the convolution of circular harmonic and a scalar, you will get um, feature map feature which cycles. Sorry. you'll get that kind of feature that I described on the previous slide. Um, and if you take the convolution of the original image with an order 2 circular harmonic, you will get uh, a feature that rotates at a frequency half that of an order 1 feature. So when you have an order 1 feature, what do you do with it? You can also convolve it with an order 1 circular harmonic and get a feature. And it turns out, this is a theorem they prove, that you can convolve a center of rotation with which cycles with rotation um, result. It has it also cycles, and it cycles with an order that's a sum of the original the filter. So the feature map order is 0, then you just get the old theorem, which says that um, you get the rotational order of the filter. But if you have a feature map which already cycles, then you they add together, and you have this kind of meta neural network. Convolve it with um, and it can, for example, go back to order 0 and not cycle at all with rotations. Um, and you can aggregate the results from all source orders and sum them up. So what exactly does convolution with a circular harmonic look like? They don't they analyze they work on um, signals on continuous functions from a pair of real numbers and another real number to a complex number. But in reality, we of course can't use those. We have to sample images, and uh, we could um, sample and then convolve on sampled images. And that's what they do, because it turns out that it's theoretically the same thing as if you just did all the convolutions somehow in continuous function space, and then sampled to get uh, into an image made of pixels. So when the time comes to perform a convolution, they take some image, they sample pixels around it, and they apply some filter to each radius of those pixels. So in this radius, for example, we have 4 pixels, and we multiply the value of each of them, their complex numbers, by a circular harmonic. Um, and the order of the circular harmonic is determined by the order of the filter. So here, if you have an order 1 feature map, we have 3 possible filters, one going to 0 rotation order, one going to 1 rotation order, and one going one higher. Uh, and they just take the value of the circular harmonic at that point and multiply it by the value of the image at that point. And when you do that, your uh, um, your center of rotation stays a center of rotation. Uh, so your whole function is still equivariant. And the filters they use, they are circular harmonics. Um, and if you just convolve with circular harmonic, it would go on forever. Um, and they instead cut it off, and then they multiply each radius by some other function. So they use a kind of low rank decomposition for the filters.
What exactly do you mean by low rank here?
By low rank, I mean instead of defining um, defining the magnitudes at each point, they instead decompose it into factor it into two functions for magnitude and one for phase, and then they multiply them together.
Right, okay.
Yeah, and for regular usual convolution filters, we don't do that. Uh, if we did, they would be slightly worse, but they do that, and they actually have about 5 times less parameters than um, corresponding convolution filters. Another thing they do is after taking the um, convolution, they have to do an activation. So the linear transformation part is done. Now comes the activation. And if they just took the ReLU on the real and imaginary parts of a complex number, um, they would not get uh, the same center of rotation equivariance properties they did before. Why? Before because uh, when you apply such ReLU, it changes the phase. So it just sets the phase of any number which does not have both real parts and a positive real part and a positive complex part to whatever you want it to be, and it sets the magnitude to 0. Um, so instead, they use a function called crelu. Crelu is a ReLU which only operates on the magnitude, uh, and it changes the magnitude to um, 0 if its magnitude is below some threshold, and uh, to the magnitude minus the bias if it's above the threshold. Um, the magnitude is always positive, so they have to put the bias into the activation function. So it doesn't just become an identity function. And here you can notice that the threshold is actually the negative bias. Uh, so they first add it, then uh, take the ReLU. And harmonic networks, so we have two operations of the big three down uh, of convolution, activation, and pooling. And harmonic networks, they don't do pooling. They instead just resample the function with a slightly lower resolution. They can't use max pooling because with max pooling you set the value to whatever the pixel with the highest magnitude was. And if you did that, then your center of equivariance would just shift to some points you don't know among four which you pull together. If you use mean pooling, your center of equivariance is just um, even less predictable. So instead, they just resample it to a lower resolution, as they already did before. Uh, yeah, as a result, you get something which um, even looks like a CNN. The surface, which takes images and performs an invariant mapping on them. And when they apply to classification, they get much better data efficiency than CNNs and CNNs with data augmentation. Um, we can't tell if the scaling laws are proved and how, because this is a 2016 paper, but I think they do. So we did all that work, taking circular harmonics to ensure that there was rotation covariance around each point, uh, and this produced this data efficiency improvement. Uh, and we can apply the same ideas to 3D, but it becomes more complicated. Uh, um, and uh, I might cover that next time. Um, um, but it's overall pretty similar. And that's all.
Okay, thank you very much. I think
Um,
I have a question, and also Honglu has one, both related to
yeah.
so the whole sampling thing. So I think Honglu's question is about, so when doing the math of equivariance, do they consider arbitrary rotations where some pixels go out of bound? And if that when that happens, do we lose that information about those pixels? So I guess the question is about, yeah, the behavior of these of your convolution, rotational convolution near the edge of the image, probably.
Uh, yeah. What they yeah, you do lose them. They take some center of rotation along which it's equivariant. Uh, so if your pixel doesn't see whatever uh, pixel is lost rotation, yes, it's gone.
Right. The, my other question is about, so when they say they sample and resample, do they like approximate the image with linear interpolation, or
I'm not sure what exactly they used to implement that. Uh,
yes, some form of image interpolation at least? Yeah, maybe they say it somewhere. I think because if we
right,
lose
I think.
information at edge pixels, then group equivariance becomes problematic because those rotations are not invertible. Right. So I guess here they solve the problem by just not doing the convolution when they would lose some pixel, right?
Yes.
Okay.
Uh, and yeah, um, that is what they do.
Yeah, interesting. Yeah, it's an interesting paper because like they use these complex numbers in the architecture, and they need to use these special value for that, which is unusual. I think I might have heard of this paper before from a colleague who mentioned, yeah, they use complex numbers and it makes things a bit more difficult.
Mm, yeah, the complex numbers they're really useful because they let you get very predictable behavior with rotation, um, and they actually implement it with a pair of real numbers. They don't use. I don't think the framework they used back then has complex numbers. Um,
But yeah, complex numbers are pretty much always just two real numbers in a trench coat. So
yeah.
okay, yeah, but it's interesting because like I was looking, so that colleague that mentioned to me, he had an approach of not equivariance but rotational invariance using Bessel functions. which
Oh,
it's a trick physicists know very well. So yeah, Bessel functions are basically some a basis of rotational invariant functions. I think they were using that for at least rotational invariant CNNs, but like it's different than this paper that does really equivariance in general. But
yeah, I think I saw some follow up which used Bessel function instead. Um, and some even use B splines. So yeah, if you can prove something useful, I don't think that circle harmonics is the only way you can uh, get covariance. It's just that they're the most general.
yeah, I guess maybe one thing I'm not sure you actually really like made clear, but maybe that's because most people know that one. But like that, you give your example of translation invariance, which is like somewhat the default of CNNs that they're known to be, if I'm not mistaken, if you do it correctly, they are just translation invariants by construction, and it's also related to the Fourier transform and convolution.
Yeah, sorry, that was push talk. Yeah,
It's not a really a reproach, but
yeah. Uh, Actually, Salgan 3 it's addressed this. Uh, when you use Rayleigh activations, they're not exactly covariant because really it amplifies the high frequency content,
right,
and you need to either anti-alias it before applying ReLU or band limit it after performing ReLU.
right. I think they do say some things about band limiting in this paper, don't they? Uh,
I think um, they just call band limiting the resampling they
right,
perform instead of pooling. I could be mistaken.
yeah, I see the paper. Um, yeah, I mean,
Yeah, they just call it band limiting for sampling the pixels initially.
right. Maybe one thing I think they mentioned in the paper that because also another advantage of doing this like equivariant stuff is that instead of having this duplicate, like the problem when you do augmentation is that you have these duplicate filters or yeah redundant filters
All
that
right, right.
like take more parameters. So I guess one of the other advantages is that doing this kind of stuff is also more parameter efficient.
Yeah, they're parameter efficient for a different reason, which I mentioned. They do a long range decomposition. Uh, so they have like 5 times less parameters, but they compensate with width and depth. Uh, and when they look at filters, they say that there's uh, less duplicate filters. Um, which, yeah, looking at inception filters, I think there are. Um, yeah, it seems to be more filter efficient overall. I forgot to include this in presentation.
I was a bit confused about that part because they have like one table about like yeah comparing their model with other ones and number of parameters and here okay they have the best test error but also they have the most parameters so it seems like if they wanted to prove that their method needs less parameters that's maybe not the unless wait is that the table I'm looking at that's table 2
All right. Uh,
right okay no I see table 2 does show that they need more less parameters for better result.
yeah, here that is the case. This is for edge detection, I think. And edge detection is a task like segmentation. So you really do want equivariance. And the features, they look nice. I can't comment on whether it's easier to interpret.
Maybe one interesting thing, I guess, here they're not just they don't have only the rotation equivariant. They also just they also keep the translation invariant or equivariant.
Yeah,
So
right.
that's also a nice thing. Like that might be tricky to have both at the same time in principle.
Mm-hmm. Yeah, I wonder if you could do somehow a combination of the Fourier transform and the circular harmonic Fourier transform, and just do all convolutions in Fourier space if you wanted really
It might be
large
possible.
filters.
I know there's like a whole cottage industry of designing group invariant networks for like any kind of group one might want. But we can probably dig that a bit further. Okay, so I see it's already the 1 hour mark. So does anyone else have questions? Yeah, so Honglu will be answered. No questions? Then okay, I guess we can leave it at that. So next week we'll be doing the second round of general topology. So I've already posted the reading earlier. So if you're interested in that, it's up there and it's more advanced topics in topology. So yeah, thank you very much, Nev, for your presentation. It was an interesting paper and an interesting presentation.
Uh, Thank you. Uh, I'm sorry if explanations were unclear. I didn't sleep very much today,
Yeah, what time
and
is
plan
it
to
for
do
you
this.
actually?
You can see it in my screen share.
Yeah, okay, so fairly late. So yeah, for considering you if you barely slept, I think that was pretty nice.
Uh, yeah, I've been sleeping for 5 hours for 3 days. Um,
Oof, too
but
hot.
yeah, read the paper. It's pretty unclear, but um, it's possible to interpret. Yes.
Cool. All right, I think we can leave it at that and maybe let you try and get some sleep. So yeah, thank you everyone. Thank you, Nev, and see you guys next week.